Hi, I'm Peter Williams. It's March 2024, and this video will give you a brief introduction to daschlab, the recommended software for interactive analysis of data from the DASCH project. daschlab is a Python package that's meant to be used in the JupyterLab environment, which is the screen that you're seeing here mainly. This is basically the Jupyter Notebook format, which is very popular with some extra features for visualization and interactive analysis, which we'll see a little bit of, which I think will help you understand why we recommend that people use it this way. So to get started, I will open up a sample notebook here with preloaded steps for just showing analysis of data from a star called RYKank, which is an eclipsing binary. So I'm not going to try to explain every line of code here. This is just meant to give you a sort of overall view of what it's like to use daschlab. So we recommend running it in a notebook. You don't have to do that, but for the sort of interactive analysis and cleaning up the data that is really necessary with DASCH, it's a very helpful form factor. So we'll start by, as usual in one of these kinds of notebooks, you'll import some modules, and then the first thing we'll do is we'll set up what we call a session, where whenever I'm analyzing data using daschlab, I define one of these sessions and I tell it a name of a directory, in this case RYKank demo, where it will store data. So that's here, and so as I'm doing different analysis steps, normally if you're doing them the first time, it will download the data from the DASCH servers and save them locally. I've already done that just to save time, so you won't see the download steps. But also, so once you've done things like this, all the data in that directory are FITS files or AstroPy ECSV files, generally pretty easy to work with, so you're not at all required to use daschlab. They're pretty straightforward formats. So in this case, I'll run these commands to sort of teach our notebook about what we're talking about, what our target is, what reference catalog you're using. As an example of why the JupyterLab environment is nice, one thing we'll do is display the catalog on the sky. So what I can do is I can open up Worldwide Telescope in its own tab. So this is something that you can do in the JupyterLab environment that a traditional standalone Jupyter Notebook can't do. I can drag that tab over here, adjust things a little bit. And this is sort of a standard or kind of Google Maps for the sky sort of interface. And this command will have my Python notebook talking to Worldwide Telescope. And for instance, when it connects, it sends the view to the location of this particular source. And then I can load up catalogs and images for display here. So the catalog, this command will get it. So I just want to show that this is an AstroPy table. So in general, daschlab tries to use existing AstroPy functionality for whatever it does. And here, anything that you can do with an AstroPy table, you can do with this catalog. I'm just showing the first few sources in the catalog sorted by proximity to my target. And what I can do using this integration is this particular command will load that catalog up in this view. And so this is sort of DASCH's list of known sources in the area, and it has an existing record for this star. You might see there looks like there's a little bit of an astrometric offset here. That's because the sort of default WWT base map, it's high resolution across the entire sky, but it does have sort of a few arc-second astrometric error. I can switch to pan stars, and then things line up a lot nicer. I can also do something like this particular source, it's my source of interest, I know what it is, but if I see something else that's interesting, I can click on it here, and it will show up in this view, and also this particular command will fetch information about it into the Python environment so that I can access what its reference number is or other information about it. And this kind of bi-directional communication where your Python notebook can send information to WWT, and WWT can send information to the notebook is really convenient for exploring data, for interactively analyzing data, and it's the kind of thing that we think makes this all worth using. So here I've loaded up a catalog of imagery, a catalog of sources. I can also load up imagery. So what these commands will do is I'll try and load up sort of a nice example dash image, and I'll do that by actually fetching the light curve data for my target of interest, and then that light curve table I can show a little bit of that. This is another AstroPy table with a lot of columns about quality metadata and things like that. One of them is the limiting magnitude in that area, so sort of how deep the plate is. And so I can basically say, okay, what are the light curve points that have a detection and also good limiting magnitudes, and sort them by that. And then I can say, so okay, these are probably the best plates in the light curve, and I can pick one here using this, what we call local ID, and overlay it. And in a second, we should pop up here. This is a cutout from the relevant plate, and we can see indeed it looks pretty nice. You do see there's some kind of, fiber or something, probably physically on the plate when it was scanned, but overall quite nice. And in Worldwide Telescope, I can do things like, due to an issue in my recording system, there will be a pop-up menu that doesn't show up, but I can use a pop-up menu and change the color map, or do things like adjust the stretch a little bit. So I can also take that light curve and then get a little summary of the actual data that we have here. So around 1,200 good quality detections in the default analysis. I can plot that. So this will use the bokeh library for plotting, which has some nice interactive features as well. So we can see the time axis here is going from the 1890s to the 1990s. We have a lot of detections, a lot of upper limits. And so since this is an eclipsing binary, these low points are plausible, these high points less so. And if I mouse over them, I'll get a little pop-up with information about the particular point, which is very helpful for being able to then sort of figure out, pull up its particular image or information about it and try and decide whether I believe it or not. I did say this is an eclipsing binary, so it has a known period, and one other thing I can do is, because this light curve is once again an AstroPy table, I can add a column that corresponds to a phase calculation and plot it using that. And so this is the same data, just with the x-axis being a phase, and we see something that looks like a nice coherent dip. And the error bars aren't plotted in this case. They're often 0.1 or 0.2 of a mag, so the sort of noise is not too surprising. So this does show, once again, these high points are a little suspicious, these low points in strange places are suspicious, and this is why we really encourage everyone, you can't just download your light curve and use it in a publication. You do have to look into the points and try and understand what's going on. DASCH data have these quality information called A flags, a standard set of A flags that is, to reject sort of carte blanche is this particular list here. And so what I can do is I can reject those A flags in my current light curve and plot again. And you'll see that a lot of these bad points have disappeared. Another kind of data quality filter that I'll almost always want to apply is a separation filter. So each light curve point has an RA deck associated with that particular detection, which I can compare to the RA deck of my catalog source, which is known. And for instance, if we plot magnitudes versus separation from that catalog position here, we'll see that there's a certain separation where above this point, the magnitudes are all looking pretty suspicious. And so as an example of that, here's one plate with one of these relatively large separations. And if I plot those data, I can see this is a much lower quality plate overall. I mean, it's at least shallower. It probably covers a much larger area, but the spatial resolution is poor. It's not as deep. And whatever the pipeline thinks it's found here, clearly it's locking on to some little noise fluctuation. That's why the separation seems large, but I don't believe any detection around here at all. And so we can reject those points. And if I plot again, we'll see that more of the bad points have disappeared. For this particular light curve, it turns out that some DASCH points, such as this one, have a low time accuracy. So this is a number that quantifies our belief in the timestamp associated with the data point in days. So this one is uncertain by a day. And this is the kind of thing that's somewhat unique to the DASCH data, where our timing of these exposures is taken from handwritten logbooks from 100 years ago. All sorts of problems can creep in, and so some points we just don't know their timing that accurately. And with an eclipsing binary, whose period is around a day, having a time accuracy that is off by a day ends up being a problem. So if we just sort of count up, okay, there's around 32 points in the light curve with time accuracies worse than 0.2 day, and we can reject those and plot again, and this bad point and a few other ones have gone away. We've got one last bad point here that is obvious, at least, and I can print out information about that one. So this is a detailed summary of a lot of the flag fields associated with it, and then that light curve table has all sorts of additional columns that you can use for things like, ellipticity, full width half max, all sorts of metadata in there. In this particular one, it's almost always helpful to take a look at the actual data again. So we'll load up that image. And so this actually is probably real imaging from the edge of a plate. The point spread functions get wild like this. And once again, whatever the pipeline thinks that it's detected here clearly is not very believable. If I look at the flags associated with this point that haven't already dealt with, the suspected defect flag is one that seems relevant and hasn't been flagged before. So we can flag that out and replot. And now our light curve is looking like the obvious outliers have been dealt with. Now, if I dig into this a little bit more, it's probably true that a lot of other points, might need rejection depending on how stringent I need to be for my particular analysis. So depending on the science application, I might go farther. So this is just sort of an overview of the kinds of things that we can do in daschlab. And once again, you don't have to use it for every step of your analysis. All these data that we have are FITS files and AstroPy tables, which we can save in all sorts of standard file formats and integrate with other tools. But hopefully this interactive environment gives you a nice way to understand your data and explore things, and also can download the data on the fly as you need them. And so hopefully it'll be a nice, convenient way to get working with DASCH. Thanks for watching.